So, um, so good day, everyone. My name is Timothy, and I'm a PhD student at the University of Adelaide in collaboration with a plant breeding company, Australian Grain Technologies. And today I'll share a little bit of my research on integrating computer vision and bivariate genomic prediction models to improve the selection of blackleg disease resistance in canola breeding programs. And I would also like to thank the organizing committee for allowing me to share my research today. So just to give a little bit of context on blackleg disease, so it's caused by a fungus known as Leptosphaeria maculans, and it's the most destructive disease in canola, causing an annual yield loss of between 10 to 15% in Australia, and in severe cases, it can cause up to 90% of yield loss. And common symptoms include necrotic leaf lesions and stem canker that causes the plant to lodge. So typically in canola breeding programs, blackleg resistance of individual genotypes have been quantified using their survival rate against blackleg disease in a disease nursery that have been infested with high disease pressure. And this survival rate is derived by the ratio of number of plants survive at maturity against the number of plants that emerge at the start of the season. And this is typically done by manually counting plants in the field, and as you can imagine, it's very laborious and time-consuming. And as the scale of disease nurseries continue to expand, manual counts have become the major phenotyping bottleneck. So the proposed solution here is to use a combination of high-throughput phenotyping using drone imaging, as well as deep learning-based object detection algorithms to automate this plant counting process. And by doing this, we can improve phenotyping efficiency and ultimately increase genetic gain for blackleg resistance. So the first part of this project is to perform drone imaging across our blackleg disease nurseries, and here I've just shown an example of a drone and a camera that we use in one of our environments. And we performed this drone imaging across 3 sites in Victoria, South Australia, as well as Western Australia across 2 years, 2022 and 2023. And here are some of the plot level images that we have extracted from the drones. And as you can see, images generated across different locations and years can look quite different compared to each other. And this can be attributed to differences in like soil colors or the amount of stubble, as well as the drone camera that was used that will ultimately affect the image resolution. And the next part of this project is to use the drone images that were collected and extract the plot level images for each genotype. And because here we have used a supervised deep learning convolutional neural network, so we go into those images and we annotate them with the canola seedlings, and we run the model through multiple iterations to train the model to learn the features and what is a canola seedling. And so to put this seedling detection model that we have trained into real-world application and to test and validate its performance, here we have used an image that has never been seen by the model on the left here, and running that through the seedling detection model, you can see that the model has actually done a pretty good job with putting a red bounding box on each and every canola seedling that it can detect, along with a confidence threshold of how confident the model is on that specific prediction. And by correlating this model predicted counts back to the manual label counts for the test set, which is essentially just a subset of images that the model has never seen in the training process. And this test set comprised of over 1,700 images across 6 environments. And as you can see, the model has done a pretty good job with achieving a prediction accuracy of 0.95. Which suggests that these deep learning-based object detection algorithms can actually reliably and accurately replace manual plant counting in a large-scale disease nursery. And the next step of this project is to optimize existing genomic selection approach using the plant counts that were generated from the disease nurseries. So historically, the breeding program has applied a univariate analysis on the survival rate, which is, if you recall previously, I'd say the survival rate is essentially just the ratio of number of plants survived against the number of plants emerge. However, this univariate approach neglects the correlation between the plant counts and their individual spatial trends. So instead, a more optimal approach is to use a bivariate analysis that accommodates both the emergence and mature counts such that it can account for the genetic and residual error correlation between these two plant counts, as well as their individual spatial trends. So this slide here, I've just shown an historic approach, which is the one-step univariate prediction linear mix model, and the phenotypic values here is just the survival rate, and then the fixed effects can be any linear global spatial trends across the paddock, and the non-genetic random effects. Here I've included some random rows and column effects as necessary, and here I've also partitioned the total genetic effects into additive and the residual genetics using a genomic relationship matrix, which I'll go into more detail in the next slide, and as well as the residual errors that have been modeled through an AR1 spatial autocorrelation model. So here I've just expanded the linear mix model from the previous slide to accommodate the two traits, which is the emergence and maturity plant counts. And all the terms on the right-hand side of the equation have now been expanded to accommodate for two traits. But here I'll focus more on the genetic and residual error effects. And here the genomic relationship matrix that I've mentioned before is derived from over 8,000 genomic markers that were filtered for minor allele frequency missing values as well as heterozygosity. And I've also used an unstructured variance covariance matrix to model the correlation between these two plant counts for the additive as well as the residual genetics. And here, for the residual errors, we have explored two different forms to model the residual variance covariance, which I'll go into more details in this next slide. So the first form of the variance covariance matrix here has been used in many multi-trait studies where you have a three-way separable structure where the trait residual covariance matrix and it will be a Kronecker with the two-dimensional separable AR1 model in the rows and column direction respectively. However, this separability assumption also means that the same spatial autocorrelation is assumed across the two traits, which often do not make sense biologically. So a more flexible approach is the two-dimensional invariant multivariate autoregressive of order 1, which I believe was Robin's idea, which was implemented in Joanne's paper in 2017. And in short, I'll just call this 2D VR1 from now on. But if you'd like to know more on the derivation of this 2D VR1 model, I encourage you to go into this seminal paper in 2017. But just briefly, so here we have a multivariate analog of the AR1 across traits, where essentially the diagonal elements give the spatial dependency between neighboring plots at each measurement time, and the off-diagonal gives the spatial dependency between neighboring plots at different measurement times. And this allows for different spatial correlation across a temporal scale. And what we've found is 5 out of 10 environments actually showed significant improvement in using this 2D VR1 model over the historic three-way separable. However, in this case, for our data set, we found that there was minimal impact on genotype rankings, so ultimately that wouldn't significantly affect the varietal selection decisions. And I've also included some other spatio-temporal variance modeling alternatives that include the tensor smoothing splines and also the P-splines that Maria spoke about earlier. And so to provide canola breeders with a useful summary of the bivariate analysis that we have proposed for the selection of blackleg resistance, here I've utilized the regression that is regression of the genetic effects that is implicit within the correlation structure, as shown in the plot on the left here, where I've plotted the maturity blobs against the emergence blobs. And here we can think of the slope of the regression line, which I've shown in blue here, which is 0.88 as the average survival rate against blackleg disease in that population of genotypes at this given environment. And now we can then define a selection measure called responsiveness as the lack of fit or the vertical deviation of each individual genotypes from the regression line, which I've shown in red on the plot here. And if an individual have a large positive deviation above the blue regression line, that means that this genotype is more responsive to blackleg disease and therefore have better blackleg disease resistance. And for any further details, I would encourage you to look at the manuscript that I published in TAG. So the main take-home message here is that drone imaging, along with deep learning-based object detection algorithms, can reliably automate plant counting at emergence. And this is also a scalable approach such that we can allow for more genotypes to be screened within our disease nurseries and ultimately increase selection intensity. And the second part, which is using a more optimal bivariate genomic selection approach with a flexible 2DIM-VR1 residual variant structure, allows for a more comprehensive analysis of blackleg resistance over the historic univariate approach, and it also allows for a novel selection measure called responsiveness. So with this improved phenotyping efficiency, we can increase selection intensity, and with the improved genomic selection approach, we can increase the selection accuracy, and ultimately the combination of these two would allow us to accelerate genetic gain for blackleg resistance in canola breeding programs. So last but not least, I would like to acknowledge some these people and organizations that have supported my PhD journey. Thank you for your attention.